I've given you an overview of how you go from the weak form to a set of algebraic equations. Let's unpack that a little bit more by going to each term in the weak form and see how they affect the algebraic equations. Let's consider the first term in the weak form here. So I've grayed out the other terms and we are focusing on this term. I need to evaluate this at x equal to L, which is the right boundary, and W at the right boundary is just W4. That's a constant. And dt dx at x equal to L is just the value at node 4. And then I need to evaluate it at the left boundary over here, and I'll get a corresponding term. Let's take a look at this term here. This is related to the flux boundary condition at the right boundary. If you recall, we say that the flux at the right boundary is given and equal to some value. And that's related to here. In fact, that's just going to be minus q times ql from the Fourier's law. Which means that when I, assemble all this into my final equations, and I've shown just, the term that multiplies W4, I will get a term where I have the gradient at the right boundary over here. In fact, I need the k. I missed out the k here. There are lots of details, lots of bookkeeping that you can trip up on, and so I'm glad, ANSYS takes care of the bookkeeping and we can focus on the big ideas. But that's not an excuse for missing out k here. And that's just minus ql. This means that because the gradient at the boundaries appears naturally in the weak form, when you have gradient boundary conditions like heat flux, or when we go into structural mechanics, the gradient boundary condition is the traction or the force, they get naturally incorporated into the algebraic equations. And for that reason, this kind of a boundary condition is called a natural boundary condition. And natural boundary condition involve the gradients of whatever variable one is calculating. And when one assembles these into a stiffness matrix, this is a compact way of writing the equations, which I introduced earlier, you can see that the flux boundary condition will get incorporated into the right-hand side. In fact, it'll go into the right-hand side over here for the equation that you write at this particular node. It won't affect the stiffness matrix, okay? And then this term gives you the flux. So this is the flux that gives you minus flux at the left boundary, which is over here. So it's giving you the flux at this boundary, and that's not known. What's done is you use that term to evaluate the flux at the left boundary, and then you can use that to check energy balance. And in ANSYS, when we compute a reaction, that comes from a term like that, and we will look at that a little bit later, because it's a very important way of checking your results, whether it's conservation of energy in this case, or when we go into structural mechanics, equilibrium.